All right, we are picking up with lesson 3.1, graphing linear functions. In the first part of 3.1, we looked at what is a linear equation? How do we know that something's a linear equation? We looked at the standard form of a linear equation. What does that standard form look like? The 5 characteristics. And then based on that, we had 5 steps to rewrite a linear equation in standard form. Today we're going to look at intercepts of linear equations, how to find those intercepts algebraically rather than just from a graph or table, and that's 3 steps altogether, and then using that to graph a linear function. And then our third part will be graphing a function by making a table, which will include solving for y, creating the table, and plotting the points. So we're going to start this with what is an intercept? What's an x-intercept? What's a y-intercept? An x-intercept officially is the x-coordinate of a point at which a graph of an equation crosses the x-axis. Where does it cross the x-axis? We're going to fill in the second blank in just a moment. Okay. Here we have this graphed function, and it's going to cross the x-axis. This is my x-axis here, and this one crosses the x-axis at 20. So the x-intercept would be is 20, is how we would write that. Okay. Now, what I find is when we write it in words like this, sometimes we can forget what that means going back and forth. So I'd like us as a class to adopt the convention to write the point, not just the x-coordinate of that point, but actually the coordinates of the whole point itself. In which case, that's going to be in the form of that x-intercept, comma, 0, because that's the coordinate. Anytime a point is on the horizontal axis, its y value is 0. Y is always 0 there. So in this case, the x-intercept, the coordinates of the x-intercept are 20, 0. And we'll find that that's the case for any linear function. Our y value will always equal 0 for x-intercept. Now with that, we can find x-intercepts not just from graphs. We define it as when it crosses the x-axis. But we can also find this from tables now because it's going to be where y equals 0. So for this problem where we're draining a pool, we want to find when does y equal 0. And y equals 0 at the point 14, 0, which means my x-intercept, if I want just the words, is 14, because that's the x-coordinate where y equals 0, in other words, where my graph crosses the x-axis. Okay. Then conversely, my y-intercept, and this is an error right here, we'll fix that in your printed, my y-intercept is the y-coordinate of the point at which the graph of an equation crosses the y-axis. The y-axis. Okay? So, again, we'll come back to the second part in a moment. Looking at this example, here's my y-axis. Where does the graph cross that y-axis? Well, in this case, it crosses at y equals 30. So the y-intercept is 30. Well, what are the coordinates of that point? I'm going to ask for this in the form of a coordinate point, and my x value for the y-axis is always 0. 0 here, 0 here, 0 here. X is always 0. So we're going to see this is going to be in the form 0, comma, the y-intercept, b. So this answer in that form would be 0, comma, 30. Or in other words, my y-intercept is where x equals 0, because x always equals 0 on the y-axis. That allows us to come to this second example and see, where does my x equal 0? Well, here's my x coordinates. X equals 0 at this coordinate point, 0, comma, 10,080. So my y-intercept, my y-intercept is 10,080. Okay, so those are our intercepts. How can we find those algebraically? What if I'm not given the table? What if I'm not given the graph and I need to find this information? Okay, and in fact, if I have an equation, one quick way, especially with standard form, to graph, instead of rewriting standard form into some other form, we can very quickly find x and y intercepts with standard form. It's one of the nice things about a standard form. So we're going to do that by using this property that an x-intercept is where y equals 0. Okay? And we're going to fill that in then. So 2x plus 4 times y equals 16, such that y equals 0. And then we're going to simplify. We simplify 2x, 4 times 0 is 0 and just poof, goes away, equals 16. And then we just solve. Number 4 is solve. I'm going to solve this by dividing both sides by 2 to solve for x. And I get x equals 8. And then I want to write that as a coordinate in the form, whatever my x-intercept is, comma, 0, because I said y equals 0. So y should be 0 in my coordinate point. In this case, that's 8, comma, 0. All right, let's do that again. I have my original equation. I'm going to let y equal 0, negative x plus 2 times 0 equals 3. So y equals 0. I will simplify. 2 times 0 is 0 and goes away, equals 3. And then I'm going to solve for x. In this case, since x is negative, I can just use my negative 1 property. Negative 1 times negative x is x equals negative 3. That's my x-intercept. We're going to write this in coordinate point format, where x is my first coordinate and y is 0. Okay, so we found our x-coordinate for each of these two examples. We're going to work these two examples all the way through. That's the whole first part, is finding x-intercept. And once you do a few of these, they're really fast and easy. Then we're going to find our y-intercept. And this is very similar. We start with the equation, except we're going to start with x equals 0. Our y-intercept is where x equals 0. So 2 x equals 0 plus 4y equals 16. And let's do the same thing here. Negative x, which is 0, plus 2y equals 3. Again, we're next going to simplify. So 2 times 0 is 0 and goes away, and I'm left with 4y equals 16. Here, negative 1 times 0 is 0 and goes away. I'm left with 2y equals 3, because 0 plus 2y is 2y. 0 plus 4y is 4y. Okay? Then I am going to solve. So I'm going to usually multiply, divide by some number or negative 1 in order to get our y by itself. In this case, I have 4 times y, so I'll divide by 4 on divide both sides by 4. So y equals 4. And here I'll divide both sides by 2. So I get y equals 3/2, which is okay. My intercept might be a fraction or a decimal. That's all right. When we're plotting points, I go ahead and this is one of the few times I do decimals instead of fractions. If this is a coordinate, it usually makes sense to write it as a decimal. So I'll actually do that in our final step. We're going to write the coordinate point in the form. In this case, x was 0 and b, my y-intercept. So in this case, the coordinate of my y-intercept will be 0, 4. And here, the coordinate of my y-intercept will be 0, 1.5. I find one great place for decimals in algebra is for plotting points. Basically only plotting points. All right. So now we know our x-intercepts and we know our y-intercepts. We can use those to graph. So I'm going to bring those down. Example 1, I have 8, 0, and 0, 4. And 0, 4. So this was my 8, 0 is my x-intercept. 0, 4 is my y-intercept. In this case, I have -3, 1 and 0, 1.5. -3, 1 and 0, oops, -3, 0 and 0, 1.5. And we're just going to plot those points. 8 is off the graph. 6, 7, 8, 0, and 0, 4. My y-intercept's on the vertical axis. And then I'm going to grab something to use as a ruler here and connect those points. Right? When we graph a linear function, we want to go all the way across the edge of the graph. All right, in example 2, we have the point -3, 0, so that's on our x-axis, x-intercept, and the point 0, 1.5. And typically we're just doing maybe halves or thirds. It's going to be a little bit of an estimate. 1.5. There we go. And then same thing, we're going to connect those with our ruler and draw across the graph. So x and y intercepts can be a pretty quick, easy, and accurate way to graph a linear function. Let's take a look at graphing by making a table, and then we will be done. All right, so to graph by making a table, first, the easiest way to do our table is to solve for y. We'll see in example 2, it's already solved for y, so I don't have any more work to do. But example 1 does need to be solved for y. Solving for y is just like solving for x. We want to get the y term by itself first. So I'm going to start by subtracting what's not the y term, the 2x. So I'll subtract 2x from each side, additive inverse property. My 2x minus 2x becomes 0. 0 minus y is -y. Right? Equals 2 minus 2x. And then solving for y means also having it positive. So this is currently negative. When something is negative and I want it positive, I'm going to use the -1 property, multiply both sides by -1. And when we multiply both sides by -1, -1 times y, -y is +y, equals, and we're going to distribute, -1 times 2 is -2, -1 times -2x is plus 2x. So this is now solved for y. Next, we're going to make a table, and you've probably seen the XY table format. We're actually going to include a little extra step here just for our unit 3, and then in the future we'll do just the little XY format. But basically we're going to choose some X values, and then we're going to evaluate to find what Y is. We're going to find out this equivalent expression to y, which in this case is -2 plus 2x. So this is the expression that's equivalent to y. And then when we simplify that, evaluate it for x, that'll give us our value of y. And then we can write that in a coordinate point format. Okay? In this case, my expression that is equivalent to y is 1/3 x plus 3. So look at our first value here. We typically want to choose some x values on the left side of the graph, some negative values, on the right side of the graph, some positive values, and 0. So I'm going to plop 0 in here. We'll do, let's say, a -1, +1, and 2. Now, always do at least 3 points, preferably 5. For space, I did 4 here. We kind of split the difference. So when x is -1, then this expression becomes -2 plus 2 times -1, or -2 plus -2, which is -4. So this coordinate point is -1, -4. When x is 0, I get -2 plus 2 times 0, which is -2 plus 0 is -2. Or in other words, the coordinate point 0, -2. When x is 1, then my y expression is -2 plus 2 times 1, or -2 plus 2, additive inverse property, equals 0, or in other words, 1, comma, 0, x, y. And -2 plus 2 times 2, -2 plus 4 is 2. So I get the point 2, 2. Looking at this, we happen to have also found a couple of intercepts. This is where x equals 0, which means my y-intercept is -2. Looking at my table, this is where y is 0, so my x-intercept is 1. Let's do the same thing for example 2. Now, we want to be careful when we have a fractional exponent of x. It's going to make sense to avoid fractions to choose values of x. They don't have to be -1, 0, 1, 2. They could be -5, -3, -2, 0, 1, 2, 8, 7. What's going to work best is to choose values of x that are multiples of this denominator. Then I'm not dividing things that will become decimals, and we can get nice integer results. So I still want a negative number. A negative number that's a multiple of 3 is, say, -3. And still 0. I don't have to worry about 0 causing any problems. And then we'll go 3 and 6. And then I avoid decimals and fractions so I can plot accurately on my graph. Looking at this first one, 1/3 times -3 is -1. -1 plus 3 is 2, which gives me the coordinates -3, 2. 1/3 times 0 plus 3, 0 plus 3 is 3, or the coordinates 0, 3. 1/3 times 3 is 1. That's the multiplicative inverse property. They're reciprocals of each other. 1 plus 3 is 4. 3, 4. And 1/3 times 6 plus 3. 1/3 times 6, this isn't 1/18, that's 6/1. 6/3 reduces is 2, plus 3 is 5, or 6, 5. So now we have a set of ordered pairs. Linear equations are continuous, so we can plot these points, -1, -4, 0, -2, 1, 0, 2, 2. and then connect them with a continuous straight line. Linear functions are continuous straight lines all the way to the end of the graph and an arrow at the end. Right? And then for this function, I have -3, 2, 0, 3, 3, 4, and 6, 5. And I will use my ruler and connect those points. Oops, my ruler's just a little bit off on my screen. Connect those points all the way off each end of the graph and an arrow to indicate that it is continuous. It's going to go on forever. And that is how we graph a linear function from standard form by making a table. Have a great night.